Welcome, everyone. My name is Pavlos Protopappas. I am the Scientific Program Director for the Institute for Applied Computational Science. You can see our banner there. Just for people that don't know what is the Institute about, just a very short introduction. We are an educational institute focused on a master's program along with the secondary field for PhD. We do that by having a very exciting curriculum. Some of the courses quite popular for data science, software engineering, stochastic methods, all the way now to extreme computing. Also, along with the courses, we have research activity for the students, and also we see ourselves as a focal point for computational science ventures. And part of that, we organize few events. One of them is the seminar series, and we're going to start in a second. And one thing you should all know is in January, we have a big festivities here, 2 weeks of workshops and challenges and symposium. Will be on our website soon, in a month or so. So the seminar series is very diverse because our focus is in the computational science, which has diverse applications. And I can talk about what's the philosophy behind it, but I want to be honest about it. We basically have talks what we think is cool. And we invite speakers that we think that they do cool things. First one will be Eugene. I will introduce him in a second. This semester, the program is up on our website. Today is Eugene Stanley. Then we have Christopher Duan from the Broad Institute. Bruce Schneider will be talking about privacy. We have Dan O'Brien will be talking about data science in the city of Boston. Then we have Sasha, a faculty here at the new faculty at CIS, who will be talking about, I guess, his natural language processing. Chris Jones from iRobot. Finally, 2 more amazing talks on the 22nd of November. Mark your calendar, is me. And then Bryce Meredith from Citrin Informatics is a company out in California that design experiments. So the program is on the website, so you can see it. So that brings me to our first talk of this series, and I would like to introduce Eugene. It's my honor to introduce Eugene Stanley. He's a physicist, and I believe in good education starting with physics, as myself too. He's a true interdisciplinary guy. He's done a lot of work in physics, but he's done work in, I was just looking at his bio and in Wikipedia and his publication. I think I can talk for 10 minutes if I mention everything that you have worked. But he started his career in solid-state condensed matter physics. He has some seminal work in phase transition and in liquid water. But one thing that struck me when I was talking to him is that he has advised 110 PhD students, and I think he knows what every student is doing. He's talking to one of his PhD students. You don't know that. He said he was a great advisor, and I think that's an honor to hear from your students, right? He has done work in, he coined the term econophysics that he's going to talk about, but one thing that struck me is that he's actually got an award for extraordinary contribution to human rights, which I think is another amazing thing. He's a member of the National Academy of Science. He started at Wesley as bachelor's. Wesleyan. Sorry, Kathy. Wesleyan. Then he did his PhD at Harvard, moved to MIT as a professor there, and then to BU, who's been there since then. Today, his talk is about how we use large data to derive empirical rules for economics. And I don't want to take more time. Let's welcome Eugene. Thank you.
Thanks very much. Do I have a mic? Did you turn on the mic?
Yes.
It's on? Can you hear me?
We can hear you.
Okay, I can't hear me. So I first apologize. Now I hear me. I first apologize that this screen is dead, as you can see. We've worked for 10 minutes trying to make it come alive, and apparently it's some glitch in the inner workings of the whole system. So those of you who are way up there may have trouble seeing this. I don't quite know what to say, except that there's about 6 seats up here in the front. And I don't mind if you sleep, so it's good. So it's an honor to come back to Harvard after 52 years, when I was a graduate student here, and the only building which existed, I think, was Pierce, where I was in physics, and Conan Hall, where I slept at night when I slept. And it's a big change in Harvard, but it's a great joy to be back. And I'm very honored that I got invited to give this talk today. The work I'll talk about indeed is done by my graduate students, so I'd like to dedicate the talk to them. They do the work, and usually they give the talks. But as most of them somewhere else by now, I get to give this talk. And I'm going to talk about what big data can do to a field which normally big data are not used as a scientific mode of inquiry, which is finance and economics in general. And so I'm going to talk about the question of, as the new title says, quantifying fluctuations, finance fluctuations, on a range of time scales from milliseconds to years, which you can multiply out as about 9 orders of magnitude. And using concepts of critical phenomena. What's that concept? That concept is that the same phenomenon on one scale is mimicked or even identical to the same phenomena on another scale. And the take-home message for those who do like to sleep is that the identical laws are found on the scale of millisecond as years. And this was a huge shock to me, and most people wouldn't even want to believe it because they think that there are characteristic scales in economics. An example is one of my physicists are never kind to each other, and one of my friends said, "Stanley, why are you studying all these big data? What matter are the big crashes? We have to know how to avoid them. So you should look at the big things." And that inspired me, because I had to show he was wrong, to study the tiniest scales. And in fact, the phenomena of big crashes occur at the millisecond scale with the same quantitative form. So now you can sleep, because you know what's going to come next. I call this phenomenon switching without switches. Crashes we always think have switches, and I go to economics conference now, and a lot of discussion is what caused the market to crash. And there's all kinds of different answers, but the possibility that it switched from going, say, up to going down without a switch is not something they talk about, because there's nothing to say, basically, and that's what I believe. The work, as I said, is not done by me. It's done by a lot of collaborators. The ones in green are real economists who know something about economics, and the work of all of them is summarized in a book that Cambridge is publishing momentarily, which we call The Rise and Fall of the, not Roman Empire, but the rise and fall of the business firm. And one of the remarkable things is that this bubble phenomenon goes back to Isaac Newton, as so many things do, because Isaac Newton lost his money in a bubble, in the South Sea financial bubble burst, and he's said to have announced to the world that I can understand everything in the world, the planets, the moon, the sun, but I cannot understand finance at all. And that's still roughly true, of course, because there's not an awful lot to understand. It's fluctuation phenomena. And we'll see that a very relevant fact is that traders who determine the price by what they're willing to pay for a given thing form coupled networks, and the interaction of coupled networks is more dramatic by far than individual networks. And we'll talk about that. And because everything's fluctuating, you can't predict the future. And therefore, what can you say? If you can't predict the future, you can't say anything. Get out of here is what a person in Wall Street once told me, because they're interested in predicting the future. And I said, that's not true. We can predict risk. We can even quantify risk. And if you can quantify risk, you can avoid losing. And if you avoid losing, others will lose, and therefore you'll gain. And it's not unlike earthquakes, tornadoes, heart attacks. Everyone goes to a doctor to learn their condition because that's correlated with, say, heart attacks. And the real take-home message is what I call data-driven discovery, 3Ds, reveals that finance fluctuations, like earthquakes and tornadoes and heart attacks, exemplify switching without switches. Okay, now I didn't remember my switcher, speaking of switches, so I have to switch by hand. And so now we start with phenomena. What is this phenomena? On the y-axis is the price of a stock average, which is in the paper every day, called the Standard & Poor's 500. 500 refers to the fact that it's the average cost of a basket of 500 big stocks. How big is defined we don't have to go into, but they're in principle the biggest, and therefore reflect the economy pretty much. And the red curve is experimental data over 40 years. As everyone knows, it goes up and it goes down, it goes up and goes down. And they're going down a lot. That's Black Monday on 19th of October, 87, before many of you were born, of course, but not before I was born. And this was a disaster day because in the US and many other countries of the world, the markets went down roughly a quarter, 25% of everybody's retirement saving was wiped off the globe. And this is very serious for people who are, in fact, in retirement. Fortunately, as you see, it came back within a year or so, and life plunged on. The bottom curve is what economists traditionally use, which is a model invented by Bachelier in 1900, 115 years ago. Bachelier was a mathematician, in fact, a student of the great Poincaré, and he model these fluctuations in the way anyone might be tempted to model it is a simple random walk. So this is the trajectory of a random walk with a bias. And you see they're not altogether different. There's downs like there, and there's ups like there, and there's downs, there's ups. There's no Black Monday. So other than that, there's not much difference. So this model is actually used today on Wall Street. My son's a trader with Goldman Sachs. He said, why not? And I said, because of things like this. And he said, oh, Dad, shit happens. Come on. And I say, you're lucky, because if your Goldman folds, you've saved enough money you won't starve. But how about all the people in retirement? And so this Gaussian random walk survives. However, it's not make me very happy, because I want to understand the real phenomenon. And so what do we do about that? Well, you can imagine we have to quantify something, and what matters, not only to retired people and to Goldman Sachs, are the change in price, and that's called the return, which is the difference between the price S at one time minus the price S at a time earlier. The earlier could be a year earlier, a month earlier, a day earlier. Every day on the radio you hear what it was yesterday and how much it changed in one day, or it could be on very short intervals, and there's television stations where you can see this return second by second by second. And usually what's calculated is actually not the difference in price, but the difference in the log of the price. So this is a fundamental quantity. Open up a time window, delta t, and look at two values of the price. Subtract them and form this quantity g. So let's see what that looks like. No one happens to have a clicker, do they? In their pocket? Uh-huh. Okay. Yeah, that's what I thought. So here's a plot of the return of g as a function of time, not for 40 years, but for only 13 or 14 years. And that's the y-axis. And here on the top is now the random walk theory, which most of you know predicts a Gaussian, and most of you know that a Gaussian is e to the minus something squared, so to get more than about 5 standard deviation is smaller than e to the minus 25th, which is 10 to the minus 8th, which is almost never, and that's what you see. No fluctuations more than 5 standard deviations. So this would be fine if there were only a few outliers. But in fact, shit happens a lot more often because you can look at the real data, and there's Black Monday where it was 20 standard deviations in both directions, by the way. And for Black Monday, there are, if you count them, 8 events, 8 times where the fluctuation was more than 10 standard deviations, and 64 times where it's more than 5 standard deviations. So 64 times when this Gaussian was wrong. That's not exactly rare. And moreover, those 3 numbers, 1, 8, 64, you can see are powers of 8 and, or more precisely, powers of 2 cubed. So each time you have the amount on the y-axis, you multiply by 2 to the minus 3 on the x-axis, which means with your own eye, you've seen an inverse cubic law. Now, that doesn't prove anything, of course, because the eye can trick you, and I didn't really count these as carefully as I did, but once I did, and that's actually exactly what happens. But it's not going to, you can't publish a paper that says, look at this graph and count these things, so you need to do a little more work. And who did that work? Were 2 wonderful graduate students. But before I show you what they exactly did, I want to emphasize something more that we can see with the eye, more qualitative, that after a big shock like Black Monday, there are aftershocks. And everyone knows this in economics, but what people didn't know is what Omori found out for earthquakes, that these aftershocks are correlated. And that's what the word Omori correlated means. And so these fluctuations are not purely uncorrelated random fluctuations, like a Gaussian would predict, or any other model where the fluctuations are uncorrelated, but instead they're correlated. So the problem is moderately, even though at first glance by eye it looks very simple, it's not quite so simple. And so I say you need a couple of good graduate students, and I was fortunate to have 2 very good graduate students, Gopi Krishnan and Pleru, now married, by the way. So there's romance in finance, as I like to say. Or at least in a physics lab, there's romance. It's hard to have romance in finance. My son, who left physics for finance, fell in love with a woman who's working there, and they're not allowed to have a relation, so they had to meet surreptitiously. So if one had to work late at night and the other wanted to work, they had to enter separate times and pretend not to know each other until they got to the floor, and they were always worried there were cameras around and so forth and so on. So that's not quite how universities work.
Did you get your son just fired?
Say again?
He's recorded this, you know.
Oh. I'm sorry, Mike. I thought it was just a joke. Okay. So when you have people who can look at lots of data, the key question is what's lots? And even in finance today, a few thousand data points is considered a lot. They're not, until recently, into big data. Big data, of looking at all the data, and they don't need to, because they say you look at enough until you see what the pattern you're looking for is. But when you look at all the data, which is every trade of every stock over a period, what they looked at, Gopi Krishna and Pleru, with 200 million data points, and they make a simple histogram of those changes, so you can see what we were looking at before, which was what? It was 20 standard deviations here, 10 here, and 5 here. And 3 points determine a straight line, and indeed, they are in those ratios, so it's indeed an inverse cubic law, and lots of other data are there too, all the way out to 100 standard deviations. That's exceedingly rare, given the value of the slope here. So what does that say? It says many interesting things. First, it says there's a law for these random fluctuations, and that's an inverse cubic law. The first time anyone said that was what they found out. So that's already moderately interesting. And the second thing it says is more of interest to people who don't even care about numbers. Whatever physics is going on to cause, not physics is the wrong word, whatever mechanism is going on to cause these big, bad, awful, rare events is quite likely the same mechanism going on for these events. So you don't need to sit around and wait for another Black Monday to get data. You could study almost any data, or for that matter, all the data. And this is the same argument used in earthquake research. Many of you know there's a law attributed to Gutenberg and Richter, which makes a plot of the cumulative distribution of the number of earthquakes as a function of the magnitude of the earthquake, the log of the magnitude, and finds a similar straight line, different slope, but the same straight line, and the implications of that, instead of waiting for big rare events and then studying the hell out of them, if there's anything left to study, one can study every event. And so there's seismic stations everywhere, recording data everywhere of every little shake, and those are contributing to understanding earthquakes. So the analogy between earthquakes and finance is fairly strong, but the plots were not appreciated to be the same. No. Okay, very briefly, those of you who know anything about phase transitions and critical phenomena know that there's a concept called universality, very pretentious word, that says that many different phenomena near a critical point have the same functional form, different quantitative numbers, but the same form, and that form is a power law. So we just saw that the histogram of price changes followed a power law. What about other histograms? And this plot is a histogram of something else, namely the size of the trade. You know, when you trade stocks, you don't just say, I want one of those and one of those, like in a shoe store, but you say, give me 1,000 of these and 100 of that, and so forth. And of course, if you're Goldman Sachs, you say, give me 1,000,000 of these and 1,000,000 of that. So that's called the trade size. And when you make the same kind of histogram, the number of trades on the y-axis as a function of trade size on the x-axis, I can do this, you again get a straight line. And again, like critical phenomena, not the same slope, not -3, but it's actually -1.5. This is the PDF. And if you differentiate a cumulative distribution function, you add 1 to the slope. So the slope of the cumulative would be 1.5, in fact, half as big as the other one. But again, extending over many orders of magnitude. Look, all the way up from roughly 10 to the -2 down to roughly 10 to the -10, 8 orders of magnitude. So this has to mean something, I guess, right? These don't just happen. And so what does it mean? So what to do is the real question. It's not completely clear what to do. And since it's not clear what to do, and since the background is physics, the normal thing is to say, well, things are correlated. Things are not independent. You wouldn't have a bad day on Wall Street if everything was independent. Half the stocks would always go up and half would always go down. So there's a lot of correlation. Let's look for correlations. In a critical phenomena, everything's correlated, strong near a critical point. So you might look, for example, at the simple analog of a spin-spin correlation function, which is the autocorrelation function of price. What's the price now, and what's the price a little time delta t later? And when you do that, you get a perfect straight line, but on log linear paper, not on log paper. So it's not a power law. And even worse, the characteristic decay time of this is 4 minutes. That means in 20 minutes, you're down already to the noise level. So there's no correlations in price. People like to say, well, if there were, they would be wiped out because people would take advantage of it. Let's not worry about the reason. Let's worry only about the question is, are there correlations? And the answer is no. However, things have to be correlated somehow for things we were just looking at. So if you look instead at the autocorrelation function, not of the price, but of the absolute value of the price, absolute value of R means the absolute value of the price, you get a straight line on log paper, and that straight line extends over more than 2 orders of magnitude, and it is not as straight as some of the other straight lines, but it's definitely saying something because it extends out to 100 days. So the absolute value of price change is going out to 100 days. That's since they don't work on weekends, that's roughly 20-day months times 5 months. So 5 months of a correlation in the volatility. And so there are correlations, but they're not simple sorts. There are correlations in the absolute value. Since it's absolute value, it's not clear how you're going to make money off of this because you don't know which is the sign. You can say 100 days from now, there'll still be a big volatility, but which direction? If I knew which direction, of course, I'd buy something and try to make a profit, but I don't. The person after whom, yes, Pablo has a question. Speak loud so they can hear you, though.
So if the absolute value was correlated, shouldn't we see negative correlation on the left?
Good question. We'll talk afterwards about that. Yeah, it's a very good point. This school of engineering, I learned, is now named after Paulson, and I assumed it was my son's boss at Goldman Sachs, Hank Paulson, which it's not. I learned just coming over here, but which is a pity because I was going to remark that he became famous for learning how you can use volatility to make money. His articles were called, on the covers of various business magazines were called "Volatility is My Friend," because normally you think of volatility as being an enemy. Okay, enough of just numbers. So what's going on here? What do we do? In physics, we make a model. Ising model is very popular because everything in physics, near a critical point, is somehow related in some at least analogy way to a simple Ising model. What's an Ising model? It's a system of units, called spins usually, which can be in a small number of states. The simplest is 2, and that's called an Ising model. And the point of this system is that at a magical ratio of the coupling strength, this system can spontaneously order. So near that magical point, there are huge fluctuations as all the little units start to cooperate and agree to order and then disagree and back and forth. So there are big long-range fluctuations. So maybe that's what's going on. So it's not terribly a big stretch of the imagination to see what would happen if we try to think of the finance of the world as a simple Ising model. They don't have to be spins. They can be objects. They can be anything. And so what are those 2 things in spins that control the situation? One is what's called exchange interaction. That merely means that if Pavlos is pointing up, and I'm... sorry, that's my Chinese... clock, but that's good to know, actually. I know where I am in the day. Thank you. Thank you. I got this as a gift in Beijing a while back, but I haven't had figured out how to get rid of it. Actually, I like it. It's very reassuring.
You may have some students.
Everybody understands it. Even I do, who doesn't speak much Chinese. So where was I, though? I forgot where I was. In the Ising model, there's an exchange interaction that tells 2 units to be in a similar state, and there's an external magnetic field which tells all the units to be more likely in one state than the other. And in finance, we have the exact 2 things. In finance, the exchange interaction that tells 2 stocks to be similar has a name, and it's called the herd effect, H-E-R-D. Herd is in a herd of cattle or something. And we know this effect is very, very real. Example might be the extreme example when a stock, which is basically worthless, and everyone knows that, but everyone's buying it, and you buy it simply because it's going up. And why not? Doesn't matter. You don't really know whether the company's any good or not anyway. You may as well buy this. It's going up. There are many examples of companies that were worthless that went up and up and up and up, and then finally they collapsed to 0. And then the second effect is the news effect. The news effect is what you read about every day on the paper, because it's very easy to say, today China's markets went down X%, and therefore the whole world went down by Y%, and X and Y have the same sign, and even comparable values sometimes. And that's called the herd effect. And why does that matter? Because that's called the news effect, because if you know the market's going to go down due to the bad news, then you're inclined to act on that. And that's exactly what the analogs of exchange interaction J and external field coupling parameter H are in this problem. So here's an example of the simple herd effect from the cover of an economics journal, The Economist. It's an economics journal for popular people to read on the tram, and you probably haven't noticed this when it came out, but it's a caricature of Wall Street in the old days before all the trading was done electronically, where people were thrown into a pit, and they talked to their boss on the phone to decide what to buy. And this one says he heard something's going to Excel, and the one next to him heard the word Excel, and the next one said Excel, and then someone, a little miscommunication, heard the word sell, and then boom, 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 everybody started to sell. And finally the reverse happened. Goodbye, goodbye, makes no sense, goodbye, bye, 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 and it's all over again. So this is a caricature. It's not exactly that. First of all, there's no pit anymore. So you might say, well, then why is this even relevant? But it is relevant because if you think the traders all over the world are connected by the speed of light, then you know what everyone's doing from the price, no matter where they are, limited only by the speed of light. Speed of light is actually a limitation in special cases, which are interesting, but not the subject of this. So when you sit at the computer screen, you're like in a huge pit, because what everyone else is doing is manifested in what you can see on the screen. And so now we're going to talk about bubbles and crashes, which is what that was a kind of introduction to. And Mandelbrot drew to everyone's attention the fact that a simple plot of the price of something as a function of time looks fairly similar on different time scales, called self-similarity. The top curve, in fact, it's so similar, I always have to read what the scale is. The top curve is periods of 1 day. That whole thing is 1 day. And the same data for 1 hour in this curve, and for 10 minutes in this curve, and for 1 minute in this curve. And the only embellishment is an embellishment by the graduate student who worked with me on this, named Tobias Price, who made a little blue circle at the local turning points, and those had to be defined carefully, and when it goes from up to down, and a red circle at the other turning points when it goes from down to up. And so this is just Mandelbrot with some circles. However, these are important circles, and the reason they're important is that those are the places where there's a switch from going one way to going another way. And so we decided to focus on those switch points, in part because I wanted to show my colleague in Israel that he was full of crap, that you don't have to just look at the big ones, you can look at little ones. And these were a set of data that Price brought with him from Germany, which had every transaction, down to the millisecond level of a given commodity. So it was 14 million data, not big data by today's standards, but it was, important thing is it was complete data. There's no more information available, which is, by the way, another nice point about big data in finance. In most of science, to get data, we rely on how much data a graduate student can be reasonably expected to get in a short period of his or her existence at Harvard University. But here, all the data are there. And moreover, now they're freely available through consortia. They weren't always that way, and we had to do various little petty thievery to get them from people who had them. But I was told not to say that. the people would be outside the door by the end of the talk, but I don't care. So what is this? This is a schematic of the same data with the same color code, red for local maxima, red for local minima, and blue for local maxima. And the only extra thing that's added is the volume. Why the volume? Because all these traders are looking at the screen and they're trying to guess when will the bottom be, because I've got to buy back in quickly, otherwise the stock will be right back up again. I'll miss the chance to make some money. And conversely, at the local maximum, the volume's also big because I have to sell quickly, otherwise I won't make any money. If I don't sell there but sell there, I'm right back where I was a short time ago. And so by focusing on these switch points, as I like to call them, switch points, we can make some progress. What can we make? We can make a plot from those data of, say, the volume, what we just looked at schematically, as a function of the number of trades, the time from the switch points, and we see a remarkable thing. We see a letter lambda. And for people with any background in phase transitions, chemistry or physics, when you see a lambda, it's reminiscent of the most classic problem in critical phenomena in the 1950s when Fairbank, Buckingham, and Keller measured the entropy fluctuations of helium. And they found this Greek letter lambda. And this Greek letter lambda turned out to be what set off a lot of focus in critical phenomena on quantifying fluctuations near critical points. So why not do the same? Why not pay a great attention to this Greek letter lambda and see what happens? So what do you do? First, you analyze it. And what you do is you find, if you make log-log plots, that there are power laws. And one exponent on the left side of the lambda and another exponent on the right side. And it's not limited to the volume. If you look at something else like the time between trades, the same thing. Now it's a dip because right at the switch points, the trades are coming thick and fast. And you again get a power law with similar slopes on both sides in this case. The power law does not extend over many, many decades. It extends over a little more than 1 decade. So you could say, well, it's not very convincing, but that's all we have. So you can be not convinced if you don't want to be, but then you don't have to listen to any more of this talk. But it's, for me, it's not an accident, and it's all there is. This is every piece of data there is. You can't say, why didn't those people get more data? So these are the real specific heat data on helium. There's your Greek letter lambda. And the reason this plot is very, very famous, and they should have got a Nobel Prize for that, is that it exemplifies, not the Greek letter lambda, that was known long before they were born, but it exemplifies the fact that in critical phenomena, you cannot know the scale. This is the same data plotted now not as a function of temperature difference from the critical point in degrees, but in millidegrees. And that's 1,000 times smaller, but you see you still get a Greek letter lambda. So these are exactly those data. That's why it's displaced upward. And you can do it over again to microdegrees, 1,000,000 times smaller, and you still get, within the error bars, a Greek letter lambda. So these are what we call self-similar, and there's a very dramatic demonstration of what self-similarity is. The curves, you cannot know, if I showed you one of these, say the middle one, you cannot know whether the axis, x-axis is millidegrees or degrees or something in between, centidegrees or 10 degrees or whatever. And so we do the same thing in finance data. And this is just that same plot again. I don't need to belabor that because and now this is the most exciting thing for me of all is that on the left, we have the sort of data I was showing you, analyzing every trade of every stock down to the millisecond level. 10 milliseconds, I guess. A 100th of a second is 10 milliseconds. And these are the kind of graphs we were looking at, power laws. On the right is the same quantities, only now looked at with much coarser data, which are readily available on the web, if you want, which is this S&P 500 data. And you see not only straight lines, but you see a similar slope, 0.42 and 0.46. and negative 0.15, negative 0.11. Now, you can quibble and say they're not exactly the same, but this is what they are, folks. You can't do anything about it. They either means nothing, because they're not the same, or it means something. And to me, what it means is that the phenomena on one time scale is having again and again over all different time scales, ranging over here, it's calculated out, 100 centiseconds in a second, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 100 days in 100 days, which is 10 to the 9th. And this is all written up in a popular way in physics world, and I'm sorry this chopped off. And that's about the main point. The main point, though, is dramatic. That the switching that you see is generic to all different scales. So it's not, so I could take that back to my friend in Israel and tell him to stick it in his brain and see how he understands it. Okay, so now we're almost finished. What's my time? Huh?
5 more minutes.
5 more minutes, that couldn't be better. So just to conclude with something very, I haven't said much about, if anything, about physics, except the lesson of log-log paper, which is a very important lesson, because straight line and log-log paper means self-similarity, which says something about the mechanism, but nothing more profound than that. So now I'm going to talk about a real physical system, which is a critical point of water, H2O, ordinary H2O. And don't worry about the axis. This is pressure against temperature near a liquid-liquid critical point studied by a computer. And the critical point is labeled CP here in the middle. And we're going to look at this along paths in the first order region. We were taught, or at least I was taught, in the first order region, a system is all one phase on one side and all another phase on another side. And that's the end of the story. But this is not the case. I think we know that there are also fluctuations. So even though we are in one phase, the system is flipping back and forth from both different phases at characteristic time scale. So this is a plot of what happens in water, nothing to do with finance, when you're near the first order line, not a critical point, the first order line, and it's color-coded, the water molecules, by their local density, their local order. The blue means ordered, and ordered means more like ice, which is a low density. 0.9 is ice, I think you know, because that's why ice cubes float. And the red is higher density, which turns out to be 1.05, 15% higher. And you see the system is not smoothly everywhere in between. It's flipping from one to the other, one to the other. If we shine a flashlight from the left, you see 2 peaks, the high density peak and the low density peak. So these are static pictures. Oh, not quite, this is a thing. But I want to show you how this looks dynamically, not for 200 nanoseconds, but for only 30 nanoseconds. So this is a picture, a movie made by the graduate student who did all the work, Tobias Kesselring and ETH Zurich. And the same color code, blue is well ordered, locally, and red is less well ordered locally. And you can even see here in this, the ordered ones form little patches, if you want to call them, of a few molecules in diameter, and the red ones form little patches. Now, as a function of time, I'm going to let this roll for 30 nanoseconds, so look carefully, and you'll see what happens. So already that ordered patch has gone away, and the reds are taking over. I like to think of this as Republicans taking over. We have a democratic country, but now the Republicans are taking over. Oops, they didn't last so long. The Democrats are coming back. Yeah, they're coming back. And the analogy is not necessarily bad, because voters listen to their neighbors. That's the exchange effect. And we also watch the television, the news, and everything else. And now the Republicans are coming back. And this is exactly how elections work. When we come, because each particle interacts with neighbors, with your environment, and with external events. So it's a good time to stop. We don't have to watch all 60 nanoseconds. That's it. Okay. So we do need to do that. So time to stop. A little take-home lesson. The real question is, can people who did not study economics and finance as a subject matter, even vaguely hope to contribute. That's the question I'm asked by many people. How can you be so arrogant to think you can make a contribution to a field that you never even took one single course in? Why don't you at least take a year or two off and study the damn subject? And, but that's not necessarily true. If you follow simple rules of humility, and one of the most humbling is to get a partner who does know something and then to respect him or her. The respect is not always trivial because they have a different idea of what's right and what's wrong. And then the second thing is, no matter what your partner says, simply get the data. Data are priceless. They're correct. They're the truth. And economics partners say, come on, we haven't, what are you doing that for? You must be crazy. And we are crazy, but you have to do that if you want the truth. And then you ask one and only question, are the data telling us something? And if so, what? And to know what the data are telling, you have to quantify everything on site, not to be timid, do aggregation where you want to and not when you don't want to, and then to relate the findings. We've talked about price fluctuations here mainly, price fluctuations, and I think once we talked about volatility, but there's other things too. And then maybe, if you're lucky enough, try to make a theory. We don't have a theory, except analogies with critical phenomena, for which there's basically no theory at all, Wilson notwithstanding, and but it's not clear we even need a theory. We want to know what the facts are. If I put my money with somebody, I don't care if they have a theory or not. I want them to know that they know what the facts are, so they won't do too many stupid things. Okay, it's a good place to stop. Take-home message: data-driven discovery reveals that finance fluctuations are an example of switching without switches. Nobody told the market when to switch, but it did it all by itself, just like in helium. No one told those little helium, oh, maybe if you believe in God, God told each one what to do, but you had to keep track of a lot of molecules if you did. So similarly here, this is an example of switching without switches. And with that, I want to stop and thank you for your attention. I hope I didn't go over.
So we have time for two question sessions.
Speak loud, they won't hear you. Soro. This is Soro Suchi from Rome, an expert in critical phenomena, among other things. But you have to stand up and speak loud. Otherwise, no one can hear you.
The question is, I see the beautiful analysis between the economic system and physical system. How to deal with the fact that normally physics has microscopic conservation laws which do not appear to have any analog in finance, which I'm not told. How do you deal with that?
Okay, conservation law. The question is a good question. There's one thing, one fact that disputes the analogy between physics and finance, that in physics you have microscopic conservation laws, and it's not clear if finance is any of that. I don't know. There's a finite amount of money that's conserved, but I don't know. That's a good question. Nor am I sure how important those conservation laws are when you're fluctuation dominated. You see, for averages, conservation laws matter, but I think of conservation laws as arising from thermodynamics and things that have averages. On a local scale, you can have a fluctuation that violates everything, you know. As my son says, shit happens. You know, you don't have to say, wait. And so big things. I mean, if I throw this pointer in the air, it's likely to come down because it's macroscopic. But if some little molecule of the Avogadro's number starts to wander up a little bit, we don't say, wait, it's got to turn around and come down quick. You know, it will violate some conservation law. So it may be a matter of the scale, but I don't know. It's a good question. Good question. Also, which conservation laws? You should study that. You're very imaginative. We were looking for something to work on. We have already one paper which we thought was worthy of a top quality journal, but unfortunately the referees did not agree with us. Yes, question?
So when you talk about changing over the different scales, doesn't that assume that everybody has the same speed of access to information?
Yes.
So would you say that potentially, for instance, when you think about high-frequency traders, who clearly have a large effect on market prices on a tiny, tiny scale, that there is no analog to those in the macro scale?
No, the last few words went away. So your first part, I think everybody heard that. When you say your question again, but speak very loud.
So when you go from down your sets of scales, you're assuming that everybody has the same speed of access to information. But we know that, for instance, high-frequency traders have a much higher speed of access to information, and they can react on a much faster timescale. Do you think that, therefore, that there is an analog of that on your multiple scale?
That's a good question. I'm actually interested in high-frequency trading. I'm a co-organizer of an annual meeting on high-frequency finance. Anyone wants to come, it's the last week of October. The registration fee is only $800 for 3 days, including a banquet on the Hudson River and so forth, because these people live well. Since I'm an organizer, I'm not planning to pay that fee, this is a question that gets asked a lot, and it's not completely clear. Let me try to think of the right way of putting it. There's no unambiguous answer. Your question's a very good one. Why should, if everything depends on accessibility to data and someone comes along with something called high frequency, which merely means you have the data faster than anyone else, then you should be at a huge disadvantage. And that may be true. Of course, you've got to keep in mind that who's making the decision is a computer, which is also fast, but not necessarily correct. I don't really know that. We worry about these things a lot. You don't have any quick answer. That's a hot new field, though. If anyone wants to work on something that's new, because a lot in finance is just old and boring. Nothing changed in a while. But this is something that's brand new, and it's not even clear it's safe. People worried that it's not safe because computers are making all the decisions, and if market can crash. And there's a phenomenon called flash crash, which I didn't bring up, but I wanted to, which is a phenomenon that exemplifies the difference between physicists and finance people. Finance people want to know a reason for it. What was the news that triggered that flash crash? And they've studied that, and they usually find there's, not usually, always so far, I think have found that there's no news that triggered that. It simply happened. But with automated trading, then you can imagine the stock goes down and instantly all kinds of other things react. And so it can go down faster, so to speak, more flash crash. And the first flash crashes started a couple years ago. People worried that it'd be happening all the time, but they're not. So I don't understand that too much either. Roughly speaking, a flash crash to a physicist is like a first-order transition, where a system flips from one phase to another because it's below its critical point. But this is not well fleshed out either. So there are several phenomena worthy of study by those of you who are not afraid of problems for which the answer may not be readily apparent, and flash crash is certainly one of them. Other question? Comment? Yes?
Have you looked at other securities besides equity?
To speak very loud and clear.
Okay.
The room has horrible acoustics.
Have you looked at other types of security besides equity, and if so, in what ways are they structurally
No,
similar
we've not
or
looked at
different?
others. And maybe we should. I have to learn what they are first. Maybe you want to collaborate. No, I'm sorry, I don't know anything. I really don't. I know they exist, but I don't know, how to get data. I don't know what the difference really is. They're just names to me.
Yeah, can you write down the Hamiltonian for that Ising model that you are using to derive your laws, or scaling laws? Can you tell me a bit more about that Ising model you want to use to infer your scaling relations?
Good point. So an Ising model, like all these models, is easy to define. You have objects that interact with others, objects, and with an external field. That's easy to say. And the Hamiltonian is therefore easy to write down. One term for the interactions and one term of the interaction with the field. So and your question was more detailed. It was the dynamics you want to know?
Yes. Maybe we should take it later.
Okay.
Yeah, say
I
please.
said if you need more details of the Hamiltonian, you can talk later offline.
Details, no.
Well, I was curious to understand what kind of solution you did for the Hamiltonian, the dynamics.
No solution, no, just watch the picture, watch the movie. And quantify the movie, of course. I don't mean just watch it. But,
The Hamiltonian is the observation, so it's not obvious that you can write one for this system. Anyway, we should talk.
there's also conservation of money. I mean, that's, and what?
Money is not concerned, is it? Is money concerned? Well, I don't think so. I'm not in action.
Money, perhaps, well,
Yes. As Bernie Sanders trying to tell us.
All right. I think let's get out of the room. Let's thank you again.
Thank you. Thank you, Tricia.